Hello, 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 hello. How are we all doing today? Hold on, I'm just checking a couple audio things. Bear with me. I hope I don't have two different audio things happening at the moment, but we'll see. Hopefully. If you hear two different audio things, do let me know, and I will be able to change all that. Let me turn the music to something a bit relaxing for the stream today. Today, we will be doing some chemistry. We'll just be going over some very basic chemistry, and hopefully it'll be relaxing and educational. We'll see. All right. But yeah, hopefully it'll be enjoyable. I hope it doesn't scare anyone. If it scares you, then I apologize for the scary chemistry. And I have hydrated. Thank you, Enter Darkness. I have some water with me right now. I couldn't find my glasses for today's stream though, so that's a bit unfortunate. But it's fine. Who needs glasses anyways? Now, shall we begin? Let me find the right page. I have the physical book in front of me, and then just old textbooks from a while back. So we'll just be using that. Okay, is the Spotify too loud, too quiet? Hopefully it should be. Let me know if there's anything I can change or improve, make better. Got the vertical mic on. Time for a Blur reading session. Blur, like the band? Yeah. Hopefully you'll enjoy it. We're literally just gonna be going through pages of a chemistry textbook, so might not be the most interesting, but it is what it is. All right, let's begin. Isotopes and relative atomic mass. Atoms were reasonably straightforward, weren't they? Think again. Here comes isotopes to confuse everything. Isotopes are the same, except for an extra neutron. Or two. Hi, reviews. How's it going? Yeah, I can't find my glasses. They're probably downstairs, but it doesn't matter. I can read anyway. I'm short-sighted, so it's things in the distance that cause me issues. I also have astigmatism, but it's fine. I'm very used to reading like this. Okay, the music. I don't know. Maybe I should turn the music down a little bit just so it's not. I want the music hitting in the between 30 and 35 range. There we go. Right. Now, let's learn what isotopes are. Isotopes are different atomic forms of the same element, which have the same number of protons, but are different numbers of neutrons. The upshot is, isotopes must have the same proton number, but are different mass numbers. If they had different proton numbers, they'd be different elements altogether. A very popular example of a pair of isotopes is carbon-12 and carbon-13. In carbon-12, the mass number is 12. The proton number is 6. We have 6 protons, 6 electrons, and 6 neutrons. Electrons, their mass is measurable, so we can just ignore that. 6 plus 6 is 12. We're adding the 6 of the neutrons and the 6 of the protons for carbon-12. Now, the difference in carbon-13. It is that we have 7 neutrons instead of 6 neutrons, so 6 plus 7 is 13, and that is our mass number. Now, relative atomic mass takes all stable isotopes into account. The relative atomic mass, otherwise known as AR, is just a way of saying how heavy different atoms are compared with the mass of an atom of carbon-12. So, carbon-12 has an AR of exactly 12. We can remember that AR is relative atomic mass. But you can just remember this as the mass at the top of the periodic table. Hi, Mars. How are you doing today? We're doing some chemistry. I'm doing well. Bit sleepy, but it is what it is. Sleepy as always. Oh no, I'm not studying. I'm doing some. How do I say what this is? Chemistry ASMR. I think that's the best way I can explain it. This is stuff that, like, much younger people would be doing. This is the sort of stuff that, like, 12 and 13-year-olds would be doing. It's about me. I didn't really, you know. So, calm chemistry. Now. So it says I haven't done chemistry in years. So it'll be a bit of a refresher then. I hope you enjoy it. How are you doing, sir? I hope you're well. Now, it's the average mass of all the isotopes of an element. It has to allow for the relative mass of each isotope and its relative abundance. Relative abundance just means how much there is of each isotope compared to the total amount of the element in the world. This can be a ratio, a fraction, or a percentage. For example, you could calculate the relative atomic mass of chlorine using the info in the table below. Now, let's work with chlorine. Over here, we have chlorine, and it has two isotopes, 35 and 37. Remember, these isotopes is just the mass of it. It's just this little number up here, and it changes based on how many neutrons there are. So this one here, 37, has 2 more neutrons than the 35. And the relative abundance is a ratio. So this means every 3 of the 35, there is 1 37. Chemistry is pretty ASMR. Oh, physics is not ASMR. I hope you guys enjoy the lurking. You might even learn something. This means that there are 2 isotopes of chlorine. One has a relative mass of 35 and the other 37. The relative abundances show that there are 3 atoms of 35 chlorine to every 1 of 37 chlorine. Now, to calculate this, you need to multiply the mass of each isotope by its relative abundance. So, we know that the relative abundance of 35 is 3, so we do 35 times 3. And we add that to 37 times 1. And then we divide them by the sum of the relative abundances. The sum is just the total amount, and 3 plus 1 is 4. So we divide that all by 4. And then that gives us our average. Well, instead of average, I'd say that's just more the relative atomic mass. 35.5. And you can find the relative atomic mass of any element using the periodic table. Relative atomic masses don't usually come out as whole numbers or easy decimals, but they're often rounded to the nearest 0.5 in periodic tables. Next page. Alright. Let's skip this one and go to... Alright. Let's go through filtration techniques. Filtration and crystallization. The components of mixtures are not chemically joined, so can be separated using physical methods. Filtration is used to separate an insoluble solid from a liquid. If the product of a reaction is an insoluble solid, you can use filtration to separate it out from the liquid reaction mixture. Now, just for a bit of recap, insoluble means it does not dissolve. It won't dissolve in a solution. But a solute will dissolve in a solution. It can be used in purification as well. For example, solid impurities can be separated out from a reaction mixture using filtration. Filter paper folded into a cone shape. The solid is left in the filter paper. Now, let's think about the size of things. Because the solid does not dissolve, it stays and collects at the bottom of this filter paper. But this filter paper has lots and lots of tiny little holes in, holes that are smaller than the solid. So, all the water can pass through. We can collect our water here and keep our solid here. Our insoluble solid, we remember that. Also, thank you for lurking, Yari. I hope you enjoyed the lurking. Have a nice lurk. Now, let's continue. All you do is pop some filter paper into a funnel and pour your mixture into it. The liquid part of the mixture runs through the paper, leaving behind a solid residue. Let's try a different technique now. Crystallization separates a soluble solid from a solution. This means the difference from this means that it is dissolved inside of the liquid. Unlike insoluble, this is not dissolved in the liquid. This one, it is, so we're going to have to use a different thing because if we tried using this technique, everything would just flow right through and we wouldn't be able to separate anything. Let's do some crystallization. Here is how you crystallize the product. Pour the solution into an evaporating disc and gently heat the solution. Some of the water will evaporate and the solution will get more concentrated. All right, let's expand a bit on this. The evaporating dish is this little bowl you can see over here. Just at this little diagram, there's the evaporating dish. Underneath here, we have a Bunsen burner. Bunsen burners are used to heat them up. We have a tripod here as well. Oh, Yuri says, I'm looking because I'm streaming, so okay, best of luck in your stream. I hope it goes well. You too. Good luck with your stream, Yari. You got this. Now, some of the water will evaporate and the solution will get more concentrated. Now, when it's talking about concentration here, it means there's more concentration of the soluble solid, not the water, because the water is evaporating. The concentration of the water is going down, and the concentration of the soluble solid is going up. Now, once some of the water has evaporated, or when you see crystals start to form, the point of crystallization, remove the dish from the heat and leave the solution to cool. The salt should start to form crystals as it becomes insoluble in the cold, highly concentrated solution. So, crystals, guys. Crystal method. Filter the crystals out of the solution and then leave them in a warm place to dry. You could also use a drying oven or a desiccator. Let's figure out what a desiccator is. A desiccator contains chemicals that remove water from the surroundings. Now, let's try a thing that uses both of these techniques. This next one will be separating an insoluble solid from a liquid and also afterwards a soluble solid. Alright, it will be with rock salt. You can use filtration and crystallization to separate rock salt. Rock salt is simply a mixture of salt and sand. They spread it on roads in winter. Salt and sand are both compounds, but salt dissolves in water and sand doesn't. This means that salt is a soluble solid because it dissolves, and sand is an insoluble solid because it doesn't dissolve in water. Now, this vital difference in their physical properties gives a great way to separate them. Here's how you would do it. The first step would be grinding up the rock salt with a pestle and mortar. This means breaking all the big bits into much smaller bits. This will allow the rock salt to dissolve in the water for the next step. Second step, dissolving. You dissolve it in a beaker and stir it. You can stir it with a glass rod if you'd like. That is the normal piece of sciencey equipment you would use for this. Step 3 would be filtering. If you remember, this is the step where we remove the insoluble solid, the sand. We're pouring it through the filter paper. All the sand will collect in the filter paper, and the salt and water will stay in the solution. And after, when we have our solution of salt and water, we can do crystallization, which will evaporate all the water, leaving behind the salt. We do that in an evaporating dish. Now, the sand doesn't dissolve. It's insoluble, so it stays as big grains. These won't fit through the tiny holes in the filter paper, so it collects on the filter paper. The salt is dissolved in solution, so it does go through, and when the water's evaporated, the salt forms as crystals in the evaporating dish. Now, let's go on to our next one. We'll now be going to chromatography. This is a different technique. It is often used for dyes and inks, paints, food coloring. We use paper for it. Let's read over it. Now, let's see how we actually do the experiment to test if you have some dyes and want to figure out what's in it. This is what you would do. First off, you would have a piece of paper. You would draw a line near the bottom of a sheet. Make sure it is filter paper, and this will be the baseline of your experiment. But remember, you have to use a pencil to do this. Pencil marks are insoluble, so won't dissolve in the solvent. The solvent in this case will be the water that we dip it into. And this means the pencil mark will not mess up the experiment and travel up the paper. Now, you add spots of different inks to the line at regular intervals. Then, you loosely roll the sheet up and put it in a beaker of solvent. For example, water. The solvent used depends on what's being tested. Some compounds dissolve well in water, but sometimes other solvents, like ethanol, are needed. Ethanol is simply a different liquid that will be used to allow the ink to travel up in a different way. Now, make sure your level of solvent if it is water or ethanol, make sure it's below the line that you drew, or else you don't want the inks to dissolve down back into the water, do you? Afterwards, you would place a lid on the top of the container to stop your ethanol or water from evaporating. The solvent seeps up the paper, carrying the inks with it. Each different dye in the inks will move up the paper at a different rate and form a spot in a different place. When the solvent has nearly reached the top of the paper, take it out of the beaker and leave it to dry. The end result is a pattern of spots called a chromatogram. Now, let's figure out how this actually works. Chromatography works because different dyes will move up the paper at different rates. Some will stick to the paper, and some will dissolve more readily into the solvent and travel more quickly. The distance the dyes travel up the paper depends on the solvent and the paper you use. You can calculate an RF value for each chemical. An RF value is the ratio between the distance traveled by the dissolved substance, the solute, and the distance traveled by the solvent, which is the sort of the water or the ethanol. You can find RF values using the formula. RF equals distance traveled by solute divided by distance traveled by solvent. So, you'd be dividing you'd measure with a ruler here, and you would divide this number here by this bigger number here, whatever it is that you measure, this length of A, R value of this chemical, B divided by A, the number you have here and the number you have here. Now, to find the distance traveled by the solute, measure from the baseline to the center of the spot. Chromatography is often carried out to see if a certain substance is present in a mixture. You can run a pure sample of the substance that you think might be in your mixture alongside a sample of the mixture itself. If the sample has the same RF values as one of the spots, they're likely to be the same. Chemists sometimes run samples of pure substances called standard reference materials next to a mixture to check the identities of its components. SRMs have controlled concentrations and purities. Now let's do some more separation techniques. This next one we will be doing is simple distillation. So, this will be separating different things inside liquids. Well, this one is. It just to separate out solutions when one thing is dissolved in a solvent. Simple distillation is used for separating out a liquid from a solution. The solution is heated. The part of the solution that has the lowest boiling point evaporates. The vapor is then cooled, condensed, turned back into a liquid, and is collected. So, let's look at this diagram. Heat comes from the bottom here. There would be a Bunsen burner under here. And then, let's guess that there's water and a different substance in here. The water, at 100 degrees Celsius, the water will all evaporate, turn into gas, and go into here. The condenser will cool it down back into water, and then we'll end up with the water here. And our other substance with a higher boiling point in here. So thank you for the water consume. I'll do that now. Oh. Stretch. Stretch complete. Okay. Now, let's continue. You can use simple distillation to get pure water from seawater. The water evaporates and is condensed and collected. Eventually, you'll end up with just the salt left in the flask. The problem with simple distillation is that you can only use it to separate things with very different boiling points. If you have a mixture of liquids with similar boiling points, you need another method to separate them out, like fractional distillation. Fractional distillation is used to separate a mixture of liquids. If you've got a mixture of liquids, you can separate them using fractional distillation. Here is a lab demonstration that can be used to model fractional distillation of crude oil at a refinery. You put your mixture in a flask and stick a fractioning column on top. Then you heat it. Now, let's have a look at this diagram. After we have our Bunsen burner down here, we heat it up, and our crude oil is in here. And then we have a fractioning column with glass rods, hottest bit of column, coolest bit of column, and we just, at different temperatures, we have them going into different sections. But you need things with different boiling points, or else you will not really, how do I say this? Yeah, when they go up here, if something that's like, if it's something, things will all separate because of this fractioning column, because they have the cooler bit at the top, hottest bit at the bottom. So they'll go, if something's if it goes up before it's hot enough, it'll go back down, it'll cool down. instead of going through here, but the things with the very low boiling points will continue going up. So this ensures that you can get it very controlled and get it exactly the temperatures you want to separate things out. The different liquids will all have different boiling points, so they will evaporate at different temperatures. The liquid with the lowest boiling point evaporates first. When the temperature on the thermometer matches the boiling point of this liquid, it will reach the top of the column. Liquids with higher boiling points might also start to evaporate, but the column is cooler towards the top, so they will only get part of the way up before condensing and running back down towards the flask. When the first liquid has been collected, you raise the temperature until the next one reaches the top. 1 second, my thing is doing something a bit strange. It wants me connected to TikTok. What I'm gonna be doing now is I'm only gonna be streaming on TikTok when I am playing games because it doesn't like me. Because I got banned from TikTok because you need when you're below 1,000 followers and you're streaming using an external thing like me, I'm using OBS. You need to be streaming at least 50% gaming content. So I'll only be doing TikTok streams when I'm doing games. Just so I don't get banned again. Yeah. Anyways, next one. We're gonna skip over the periodic table. And we're gonna go on to ionic bonding. Here we go. This should be easier to read. Ionic bonding. Some atoms are keen on getting rid of some of their electrons. Others want more. That's life. And ions. Simple ions form when atoms lose or gain electrons. Ions are charged particles. They can be single atoms, for example, sodium plus, or groups of atoms, for example, nitrogen oxide, nitrous oxide, nitrogen oxide -3. I think it's nitrogen. No, it's nitrogen. I just forgot the name of what it is. Nitrous oxide, I'm guessing. It is. Negative ions, anions, form when ion atoms gain electrons. They have more electrons than protons, because electrons have a negative charge. Positive ions, cations, form when atoms lose electrons. This means they have more protons than electrons, and protons are what causes the positivity. You can remember this. Protons, P, S stands with a P. P is positive. Now, anions and cations, you can think that, okay, we all love cats. Cats are positive. Cats make you feel positive, so that's why cations will always be positive ions. The number of electrons lost or gained is the same as the charge on the ion. For example, if 2 electrons are lost, the charge is 2 plus. If 3 electrons are gained, the charge is 3 minus. Oh my gosh, thank you. Thank you for the sub, Apariato. Yes, educational content. Half a year went by. Oh my gosh, yes, I've been streaming for half a year. God damn. Thank you for the sub, much appreciated. I've been streaming for a while, haven't I? But I'm really happy with the progress I've made with streaming. I think I'm doing great. It's not crazy growth, but it's slow and consistent, and that's how I like it. Hi, Saul. How you doing? Huh? Huh? Qu'est-ce que c'est? Are you enjoying the chemistry? Really, I'm trying my best to post on different socials and clipping, and I actually made my first YouTube video. I don't think you guys saw it. Hold on. Let me just make a new tab. give me 1 second. I can share my YouTube video in chat if you guys want to have a look at it. It's a comedy thing. Um, sorry, give me 1 minute. It's called Gamble a Girlfriend Spends All Your Money and Explodes ASMR. I thought it was very funny. I have so many other scripts, guys, but I just haven't been able to edit them and stuff. But here's the link to the video. Let me read out some of the names of the other scripts I have planned. That's so silly. Just go into my drive, go into my ASMR folder, go into my scripts folder. Okay. First off, we've got wife sacrifices you to a mutant hamster for saying 6'7". And then we have Valorant girlfriend beats you to death with a pan after you go 023/1. And then realistic catgirl ASMR. And then nerdy girlfriend teaches mice Scrabble and they start a nuclear war ASMR. And then League of Legend girlfriend beats you with a metal pipe after you play Draven ADC. Goth girlfriend reads you ancient demonic scripture and you explode ASMR. And then there were 2 I did that I don't think would be a good idea for me to actually write the full scripts of, because they might be like really bad. But one is girlfriend finds out you're in the Epstein files ASMR. And another one is girlfriend finds out you're friends with P. Diddy ASMR. And then girlfriend drives a car off cliff because he put Taylor Swift on ASMR. Girlfriend breaks up with you and gets with Lord Farquaad ASMR. Fujoshi girlfriend with a gun and convinces you to read yaoi ASMR. Clumsy girlfriend pilots a Convair B/36 Peacemaker and you both effing die ASMR. Conspirational theorist girlfriend says the moon landing was fake and then the moon lands on her and you all effing die. Yeah. I'm probably gonna delete some of them. I'll get rid of the conspiracy theory one. Mm, hmm. Yeah, but those are some of the ideas I have. Most of the scripts are written. I spent like an hour on each script, but I haven't like had the time to record anything. Aside from the main one, I'm a bit nervous as well. Anyways, we're getting distracted, aren't we? We are supposed to be doing chemistry. Now, to think about the charges, it's a bit strange to think that, like, giving away is positive, gaining is negative. But let's think about it this way. So, think about it in terms of being a good person or not. If you give away your things to help other people, it's a good thing to do. It's a positive thing to do. But if you take things from other people, it's a bit of a negative thing to do. So, taking things away and gaining electrons is negative, but giving away things and gaining electrons, but giving away things is positive. Giving away your things is positive, taking them is negative. Yes, yes, yes. Now, you can predict the ion's form from the group number. Groups are the vertical columns. So this is group 1, this is group 2, this is all group 3, this is group 4, this is group 5, this is group 6, this is group 7, this is group 8, and then this is group 0. These are your noble gases. Okay. Group 1, 2, and 3 elements are metals. They lose electrons to form positive ions. You have to think about this as the outer shells of electrons. For if it's easier for them to have a full outer shell by giving them away or gaining them. For example, group 7 will always want to take electrons from other things because it's easier for them to gain 1 electron than to give 7 away. And for group 1, they want to give away 1 electron because it's easier for them to give away 1 electron than to gain 7 more. So, Group 5, 6, and 7 elements are non-metals. They gain electrons to form negative ions. Elements in the same group all have the same number of electrons in their outer shell, so they can all lose or gain the same number of outer electrons, and this means that they form ions with the same charge. You don't have to remember what ions most elements form. Nope. You just have to look at the periodic table. But, here are some trickier ions that you just have to learn by memory. Silver is a +1. Iron 2 is a +2. Pb. I forgot what Pb is. Oh gosh. Chemistry teacher doesn't know what's going on. Nitrogen H. Ammonium is NH4+. Remember, ammonium is the stinky gas. Nitrates are NO3. Cu2, that's copper. Fe3+, Cn2+, hydroxide, OH- carbonate, CO32- sulfate, SO42-. Now, the transfer of electrons produces an ionic compound. When a metal and a non-metal react together, such as when group 1 metals react with group 7 elements, the metal atom loses electrons to form a positive ion, a cation because cats are positive. And the non-metal gains these electrons to form a negative ion, an anion. Remember, non-metals are on the right mainly, metals are on the left. These oppositely charged ions are strongly attracted to one another by electrostatic attractions. This attraction is called an ionic bond. The reaction of sodium and chloride is a classic case of ionic bonding. The sodium atom gives up its outer electron and becomes an Na+ ion. So, sodium is in group 1. So it has one extra electron in its outer shell. It gets rid of that and becomes positively charged. And the chlorine picks up the atom from the sodium, and then they bond. Now, ionic compounds. You can work out the formula of an ionic compound. Ionic compounds are made up of a positively charged part and a negatively charged part. The overall charge of any ionic compound is 0. So, all the negative charges in the compound must balance all the positive charges. You can use the charges on the individual ions present to work out the formula for the ionic compound. Example: what is the chemical formula of calcium nitrate? First off, you write out the formulas of the calcium and nitrate ions. Calcium is Ca2+, and nitrate is NO3-. You have to work out the ratio of calcium to nitrate that gives an overall neutral charge. So, we can see that the calcium has a 2+ charge and the nitrate has a -1 charge. So, this means you need two nitrates to balance off 1 calcium. So, your formula would be Ca and then in brackets NO3 2 times 2. Now, ionic compounds all form in similar ways. You can use dot and cross diagrams to show what happens to electrons when ionic bonding happens. Let's have a look at these diagrams. So, here's the sodium chloride one we saw earlier. The sodium gives up its outer one to the chloride and they become bonded. Aluminum chloride. The aluminum atom gives up its 3 outer electrons, becoming an A3+ ion, and the chlorine atoms pick up the 3 electrons, becoming 3 Cl ions. I feel like this one explains it a lot easier. So, the aluminum here He also has 3 extra ones in its outer shell, and it gives 1 to each of the chlorines, because chlorine is in group 7. So chlorine needs only 1 more electron to fill its outer shell. So we have 3, it's a ratio of 3 to 1. Magnesium oxide. Magnesium has 2 electrons in its outer shell that it wants to get rid of, and oxygen is in group 6, so this is perfect. This means that the magnesium gives away its 2 electrons to the oxygen. So the magnesium is positively charged, and the oxygen is negatively charged, and this attracts them together. You know, magnets always have a positive side and a negative side, and the positive side is always attracted to the negative side. Now, sodium oxide, Na2O. So, for this it's slightly different than the sodium chloride because we have 2 sodiums instead. 2 sodiums give up their outer electrons, becoming 2 Na plus ions. Their oxygen atom picks up the 2 electrons, becoming an O minus 2 ion. So it's a ratio of 2 to 1. Every 1 oxygen, there needs to be 2 sodium to neutralize the overall charge. Ionic compounds have a lattice structure. Compounds with ionic bonding always have giant ionic structures. The ions are held together in a closely packed 3D lattice arrangement by the attraction between oppositely charged ions. The electrostatic attraction between oppositely charged ions is very strong because a lot of energy is needed to overcome the strong attraction. This means that ionic compounds have high melting and boiling points. Ionic compounds are not electrical conductors when they are solid, but if you melt them or dissolve them in water, they are able to conduct electricity. Does anyone know why this is? It's because you need electrons that are delocalized too for the electrical current to be able to run through them. But here they're all close together, so they don't have any freedom. Now, let's look at the next page. Like, covalent bonding is the same as ionic bonding, but instead of that, they just share. They just share atoms, or they share electrons instead. For instance, 2 chlorines, would share one of their outer electrons and become bonded. What should we do now? Let's skip to let's try alkali metals. Group 1 elements are known as the alkali metals. As metals go, they're pretty reactive. Group 1 elements all react in a similar way with water. Simple reactions can be used to work out if an element is part of the same family as other elements. Elements of the same family will react in a similar way. For example, when lithium, sodium, and potassium are put in water, they all react vigorously. The reaction produces a metal hydroxide solution. This solution is alkaline. This is why group 1 elements are known as the alkali metals. The reaction of alkali metals with water also produces hydrogen. This is why you can see fizzing. These reactions can be written as chemical equations. For example, for sodium, the equation is sodium plus water turns into sodium hydroxide plus hydrogen. You have to remember, though, that it makes hydrogen gas. Group 1 metals can also react with oxygen in the air to form metal oxides. Different types of oxide will form depending on the group 1 metal. Lithium reacts to form lithium oxide, Sodium reacts to form a mixture of sodium oxide, which has 2 sodiums and 1 oxygen, or sodium peroxide, which has 2 oxygens instead of 1 oxygen. Potassium reacts to form a mixture of potassium peroxide, which has the 2 oxygens, and potassium superoxide, which only has 1 potassium and 2 oxygen. Now, with these group one elements, they just become more reactive the more electron shells they have. This is because it's all to do with the outer shells, if that makes sense. It means it's easier the farther away the outer shell is from the positive center, which has the protons in, the easier it is for them to lose the outer electron, which means they are more reactive because they can react more easily. Group 7, the halogens. The elements in group 7 of the periodic table are called the halogens. As the atomic number of the halogen increases, the elements have a darker color and a higher boiling point. This means at room temperature, chlorine, Cl2, is fairly reactive, poisonous green gas. Now, do you remember why chlorine travels in pairs? It's because it bonds covalently, which means 2 chlorines can share their outer electrons and both fill the outer shells. Bromine, Br2, is a poisonous red-brown liquid, which gives off an orange vapor at room level. Iodine, I2, is a dark grey crystalline solid, which gives off a purple vapor when heated. This table shows how the properties of the elements in group 7 gradually changes as you go down the group. Now, let's look at them. Have a look at this table, eh? Also, thank you so much for the water. Let me have a little sip real quick. Water consumed. Alright. Chlorine. Atomic number is 17. It's green. Its gas at room temperature, and its boiling point is minus 34 Celsius. This means it has to be, it just basically means it turns into gas at anything above minus 34 Celsius. With bromine, though, it's a big change. The atomic number is 35, it's reddish brown, it's a liquid at room temperature, and for it to turn into gas, it needs to be above 59 degrees Celsius. And iodine, this one, another big jump. Its atomic number is 53. It's dark grey, solid at room temperature, and for it to turn into a gas, the temperature would have to be above 185 degrees Celsius. Big change, eh? Now, this is the complete opposite to group 1, the alkali metals. In the alkali metals, as you go down the column, it's more reactive. But with group 7, as you go up the column, it's more reactive. So, let's figure out why. Reactivity decreases going down group 7. All group 7 elements have 7 electrons in their outer shell. They can gain 1 electron to form a 1- ion. The easier it is for a halogen atom to attract an electron, the more reactive the halogen will be. As you go down group 7, the halogens become less reactive. It gets harder to attract the extra electron to fill the outer shell when it's farther away from the nucleus. The atomic radius is larger. Hi, anime lover. I think you'll find this stream very useful for you. We're going over a bit of chemistry. Now, let's look at this little diagram and explain it a bit more. The center of this is positive. All the electrons the X is around are negative. And the less of the negativity there is, the easier it is for the middle part here to attract other things. Imagine the electrons forming a sort of shield around the nucleus, preventing the positivity from attracting other negative things. Now, let's go for some displacement reactions. The halogens are a pretty competitive lot, really. In fact, the more reactive ones will push the less reactive ones out of a compound. How uncivilized. Has nobody ever taught them that it's bad manners to push? Anime lover says, oh my gosh, my brain hurts. Oh, don't worry. Trust passive absorption. This will help you understand. This is all, yeah, you'll probably learn all this when you're like 13 and 14-ish. Or even less than that. So, more reactive halogens we remember, are group 7 in the periodic table. They will displace less reactive ones. And if we remember, the ones at the top are the most reactive. And as you go down and down and down, they become less reactive. This is the opposite of group 1 alkali, where the further down you go, the more reactive. The elements in group 7 take part in displacement reactions. A displacement reaction is where a more reactive element pushes out or displaces a less reactive element from a compound. For example, chlorine is more reactive than iodine because it's higher up group 7 and it has less electrons protecting its nucleus. So, if you add chlorine water to potassium iodide, this iodide solution, the chlorine will react with the potassium in the potassium iodide to form potassium chloride. So, iodide, it's iodine. Iodine is farther down in group 7, so less reactive than chlorine. So, if you have potassium iodine chilling and you add chlorine, the chlorine will be like, go away, iodide. And then it'll become potassium chloride instead. Now, the iodine is displaced from the salt and gets left in the solution, turning it brown. If we remember earlier, we learnt about the colors. The color of iodine. Let's go back to this page real quick. Iodine is darkish gray. Bromine is reddish brown. Chlorine is green. The table below shows what happens when you mix different combinations of chlorine, bromine, and iodine with salts, potassium chloride, potassium bromide, and potassium iodide. So, if you start with chlorine water, if you add if you add chloride solution, nothing happens because it is the same. If you add bromide solution, the bromine will just stay in the water and everything will turn orangey browny. And if you add potassium iodide solution, there'll be a brownie solution formed. And the same goes down, 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 no reaction, that sort of thing. Because, yeah, just imagine chlorine displaces all the other stuff in this one. Now, halogen displacement reactions involve transfer of electrons. You can show the displacement reactions between halogens and salt solutions as equations. For example, chlorine dissolved in a solution plus potassium iodide goes to iodide and then potassium chloride, which is the same one we saw up here. Now, Each chlorine atom in the chlorine molecule gains an electron to form two negative Cl ions. Two iodide ions lose an electron each and then form a neutral iodine 2 molecule. A loss of electrons is called oxidation. A gain in electrons is called reduction. Now, we remember this by the little phrase oil rig. Oxidation is loss of electrons, reduction is gain. Little text things like this make it easier to remember. In displacement reactions, reduction and oxidation happen simultaneously. For example, in this reaction, chlorine is reduced and iodine is oxidized. Chlorine is reduced. So, chlorine over here. Reduction is gain. It's becoming reduced, so it's gaining electrons. So look at each chlorine atom that gains 2 electrons to form positive there. Now, an oxidizing agent accepts electrons and gets reduced. So here, chlorine is an oxidizing agent. A reducing agent donates electrons and gets oxidized. So, iodine is a reducing agent. Reactions where reduction and oxidation happen at the same time are called redox reactions. You just gotta imagine that with the agents, they're just the opposite of the oil rig. You just gotta flip them around. So, next part, let's go to gases in the atmosphere. The atmosphere is mostly nitrogen and oxygen. For 200 million years or so, the atmosphere has been about how it is now. 78% nitrogen, 21% oxygen, nearly 1% argon, and 0.04% of carbon dioxide. But there can be a lot of water vapor too, depending on where you are. Make sure that you know the proportions of each gas. Good knowledge to have. And Amelia says, thank you. Thank you that you're streaming. If you were not live on YouTube, we would never meet. Yeah, I do, I do streaming on lots of different sites to make my streams accessible to people who use different platforms. I will only be streaming on TikTok when doing gaming streams, though. I hope that this can help you learn some things. Now, this is about gases in reactions. When you burn something, it reacts with oxygen in the air. When an element is burnt in air, it reacts with the oxygen to form an oxide. These oxides can have either acidic or basic character. Here are some examples you need to know. Now, magnesium. Magnesium burns with a bright white flame in air, and the white powder that is formed is magnesium oxide. Magnesium oxide is slightly alkaline when it's dissolved in water. Now let's look at the equation. If we look at this equation, we have 2 magnesiums on this side, 2 magnesiums on this side, 2 magnesium on this side, 1 oxygen on this side, and 2 oxygens. Oh, I'm lagging a bit. Oh gosh, I'm sorry. It should be okay now. Okay, my frames are no longer dropping. It should be fine now. I apologize for that. My PC is trying its best. Anyways, this equation is balanced because we have the same amount of each thing on each side. Now, hydrogen burns very easily in oxygen. In fact, it can be explosive. It has an almost invisible pale blue flame, and the only product is water, as water vapor. So, 2 4 hydrogens plus 2 oxygen goes to 4 hydrogen and 2 oxygen, balanced again. But impurities in the air can cause hydrogen to burn with a yellow flame, because this means that there are different things in that air aside from hydrogen, which messes with the experiment slightly. Now, there's a very famous test that is always spoken about to test if there's hydrogen or not in the air. Well, not in the air, but in like a carefully contained area. The combustion of hydrogen is often used as a test for hydrogen gas. In small amounts, the resulting explosion gives the characteristic squeaky pop. Alright, let's imagine we have a upside down beaker, and we suspect it is full of hydrogen. So, if we light a splint and put the flame to it, there should be a pop sound, and that will confirm that there's hydrogen. Now, sulfur. Sulfur burns in air or oxygen with a pale blue flame and produces sulfur dioxide. Sulfur dioxide is acidic when it's dissolved in water. Now, let's think about alkali and acid. So, there is a sort of scale for this, and if it's below 6, then it is acid. If it is above 8, it is alkali. And then the area in the middle is a bit of a grey neutral zone, if that makes sense. But if it's high, then it's alkali. If it's low, then it's acid. The thermal decomposition of metal carbonates produces carbon dioxide. If you heat a metal carbonate, you get carbon dioxide and a metal oxide. This is an example of thermal decomposition, which is when a substance breaks down into simpler substances when heated. Copper 2 carbonate is a green powder that will easily decompose to form carbon dioxide and copper 2 oxide when you heat it. Here is the equation for the thermal decomposition of copper 2 carbonate. Copper 2 carbonate turns into copper oxide plus carbon dioxide. To do this experiment, heat copper 2 carbonate, then collect the gas that is given off in test tubes. The gas that is collected can then be tested to see if it is carbon dioxide using the method on page 53. We'll look at that another time, not today though. Anime lover says, I'm so confused, but I like your streams. So I hope this, if you can see the stream, then you should be able to read along. If you need any terms explained, I can explain them to you. Now, we've got a test tube here. This is where the carbon dioxide collects. And under here, we burn it up. Imagine a Bunsen burners here. We heat this up. It goes dot, 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 dot. It breaks into something simpler. Then the carbon dioxide goes through here, down into here. This at the top here will be sealed with this little straw going in to avoid all the carbon dioxide just evaporating back into the air. Now, what should we do now? Let's do reactions of metals. Actually, no, let's do both these pages. You've probably heard already of carbon dioxide. It's always in the news. This will explain why. Carbon dioxide is a greenhouse gas. The temperature of the Earth is a balance between the heat it gets from the sun and the heat it radiates back out into space. Gases in the atmosphere, like carbon dioxide, methane, water vapor, naturally act as a insulating layer which keeps things in, which keeps the heat in, if that makes sense. They are often called greenhouse gases. They absorb most of the heat that would normally be radiated out into space and re-radiated in all directions, including back towards the Earth. So, let's look at this diagram. Lots of heat energy is coming from the sun. It goes into Earth, and normally some of it is supposed to go back into space. But because of all the carbon dioxide and methane in the world, it blocks it. The sun can penetrate it, but everything can't go back into space, and this is why the world is heating up slowly. Human activity affects the amount of carbon dioxide in the atmosphere. Some examples include deforestation. Fewer trees mean less carbon dioxide is removed from the atmosphere via photosynthesis. If we remember photosynthesis, it is how plants make energy. And plants make energy by taking carbon dioxide from the atmosphere and then giving out oxygen as a waste product. So the less trees there are, the less photosynthesis that is happening, which means that the less carbon dioxide is being removed. And now, burning fossil fuels is also burning fossil fuels also increases the amount of carbon in the atmosphere. It burns when you burn them, it releases all the carbon that was locked up inside these. Imagine a big box being when you burn them, let's say you burn a big chest. And after you burn the chest, it opens, and then all the carbon dioxide comes out into the air. Now, it is because of this human activity that over the last 200 years or so, the concentration of carbon dioxide in the atmosphere has been increasing. For this to have happened, carbon dioxide must be being released into the air faster than it's being removed. This is linked to climate change. Now, increasing carbon dioxide is linked to climate change. There is a correlation, or just a relationship, between the increasing levels of carbon dioxide and the gradual heating up of the Earth's atmosphere, global warming. Although the Earth's temperature varies naturally, there's a scientific consensus that the extra carbon dioxide has caused the average temperature on Earth to increase. Global warming is a type of climate change and causes other types of climate change. For example, changing rainfall. It can also cause severe flooding due to the polar ice caps melting, which makes the sea level rise. Now, let's have a look at this little chart over here. Now, 0 is this present day, and this is the temperature difference, and this is the atmospheric carbon dioxide pressure. If we look at this, in the present day, the atmospheric carbon dioxide pressure is 400, but if we go back to 250 years, it was around, like 300 or so. So we can see it's going up, 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 up. And the temperature difference over here, you can see a bit of a difficult graph to understand since there are two y-axes. I think this might have been better if there were two separate graphs. Now, and I love it says, I love this. I listen to you and write it down like you said. Mhm. When you write this all down, make sure you check over it. And when you check over it, it helps you remember things. Because often, if you write things down and forget about them, then you just forget about it. It just gets out of your memory. But if you take a minute or so just to look back at your notes, it can really help you remember things. Now, let's look at the reactions of metals. Reactive metals tend to do exciting fizzy things when you drop them into either acid or water. How metals react with acids tells you about how reactive they are. Some metals react with acids to produce a salt and hydrogen gas. You can use the reactions of different metals with dilute acids to work out how reactive they are. The more reactive the metal, the faster the reaction will go. Very reactive metals, for example sodium, react explosively. You can carry out a practical to investigate the differences in reactivity of a variety of metals by using their reaction with acids. First, set up 3 boiling tubes and fill them with equal volumes of dilute hydrochloric acid or dilute sulfuric acid. Then, place pieces of magnesium, zinc, and iron in separate test tubes. Now, these are hydrochloric acid and sulfuric acid, these are our acids. And then magnesium, zinc, and iron, these are our metals. So if you look at our little thing up here, acid plus metal turns into a salt and hydrogen gas. Now, in experiments, we always have to make sure that it is controlled. And to control experiment, things have to be the same volume, you have to use the same equipment, same temperature for things, same pressure in the air, all those sort of things. Make sure you clean out your things beforehand so there's no contamination. So this is why you have to make sure the shape and size of the metal pieces are the same. The speed of reaction is indicated by the rate at which the bubbles of hydrogen are given off. The hydrogen is confirmed by the burning splint test. The magnesium should give the loudest squeaky pop because it has the most vigorous reaction producing the most hydrogen gas. Now, since magnesium is in group 1, it is the most reactive and it's at the top of group 1. So the top of group 1, the most reactive, going down is least reactive, but in group 7, it starts with most. Yeah, wait, I'm code tweaking, sorry. This is interesting. Okay, I was under the impression that magnesium should not be very active since it's high up to the top of group 1. But magnesium is more reactive than zinc and iron, that is why. Ah, yes, that is why. But if we were using magnesium and other things instead of zinc and iron, then magnesium would not be the most reactive. It's only the most reactive in this situation because zinc and iron are in group 3. That made me have a brain thing. A brain blah for a second. Alright. Some metals also react with water. The reaction of metals with water also show the reactivity of metals. This is the basic reaction. Metal plus water turns into a metal hydroxide and hydrogen gas. Or less reactive metal plus steam turns into metal oxide plus hydrogen. Very reactive metals like potassium, sodium, lithium, and calcium all react vigorously with water. The amount of energy given out by the reaction increases with the reactivity of the metal. The reaction with potassium gives out enough energy to ignite hydrogen. Less reactive metals like magnesium, zinc, and iron won't react much with cold water, but they will react with steam. You could show this in the lab using this experiment, but even less reactive than magnesium, zinc, and iron is copper, and copper won't react with either water or steam. There is a reactivity table somewhere in here that we can. Yes, here is the reactivity series. So we look at the top here. Most reactive potassium, if we go all the way down here, copper is not very reactive, silver and gold are not reactive at all. This is why silver and gold are used for jewellery, because they aren't reactive. So they won't react with things in the atmosphere that could harm us. I think I will do one more page and then I will be heading off since my throat is very much hurting now. Now, the reactivity series lists metals in order of their reactivity towards other substances. Make sure that you learn this list. The reactivity series. Potassium is the most reactive, followed by sodium, lithium, calcium, magnesium, aluminum, zinc, iron, copper, silver, gold. A more reactive metal displaces a less reactive metal. This is like the displacement of group 7 that we remember earlier. How chlorine would displace other things like iodine and bromine. Now, more reactive metals react more strongly than less reactive metals. This means that a more reactive metal will displace a less reactive metal from its oxide because. Oh, sorry, my throat is. Oh, gosh. This means that a more reactive metal will displace a less reactive metal from its oxide because it will bond more strongly to the oxygen. For example, iron would be displaced from iron oxide by the more reactive aluminum. Let's look at our graph again. Aluminum is higher up, so it is more reactive than iron. As we can see here, aluminum is fairly reactive and iron is not very reactive. Iron oxide plus aluminum would change into aluminum oxide and iron. Displacement reactions like the ones above are redox reactions. This is because the metal is oxidized and the displacement and the displaced metal ion is reduced. Now, remember, oxidation, we remember oil rig. Oxidation is loss. Reduction is gain. Oxidation is loss. Reduction is gain. Metal compounds like copper sulfate, zinc chloride, and sodium chloride are metal salts. If you put a reactive metal into a solution of a less reactive metal salt, the reactive metal will replace the less reactive metal in the salt. For example, put an iron nail in a solution of copper sulfate, and the more reactive iron will kick out the less reactive copper from the salt. You end up with iron sulfate solution and copper metal. This is because if we look at our little table up here, copper and iron is more reactive than copper. So thank you for the stretch. Let me stretch real quick. I'll finish this page and maybe do one more, and then I will be heading off to do some cleaning. Because chores must be done. Now, if a piece of silver metal is put into a solution of copper sulfate, nothing will happen. This is because the more reactive metal, copper in this case, is already in the salt. This could also be with, let's say we have a sodium in a salt, and then we have like an iron nail put in. Nothing will happen because sodium is higher up on the reactivity series. But if we switch this around, let's say we had a copper salt, and then we added sodium. Then the sodium would displace and the sodium would become the salt. Now, if a reaction occurs, there will be a change in temperature. A more reactive metal will give a greater change in temperature than a less reactive metal. You can use displacement reactions to work out where in the reactivity series a metal is supposed to go. For example, if you were given a lump of mysterious metal, you could try reacting it with different metal, oxides and salts. If it reacted with copper oxide, you'd know it was higher in the series than copper. If it didn't react with magnesium sulfate, you'd know it was lower than the magnesium in the reactivity series. So hi Greenie, I hope you I don't normally do this normally I'm reading books. At the moment I'm going through Good Omens yeah, in my reading, but I felt today, you know what, we should go over some chemistry basics. I think tomorrow I might either do chemistry or biology. I hope you're enjoying it so far. Give me 1 second, I just need to check something. Right, we're back. And my was, yeah, I'll be here waiting for you for your life. I always stream at 6 to 7 p.m. British time. I'm English, so yeah, those are my normal timings. I should probably list them down in other time zones, but I'll figure it out. I'll figure it out another time. Now, let's go to Don't Feel Like Doing Iron. Hmm. We are going to switch to tests. Now, these are very interesting. Now, if we remember earlier, we have cations and anions. Cations are always positive because, if we think about it, cats are a positive thing. But anions, they're negative, as there's no cat in there, and when there isn't a cat around, we're always sad. Now, let's do some tests. Hydrochloric acid can help detect carbonates. To test for carbonates, add dilute hydrochloric acid, HCl, to your test sample. If carbonates, CO3 2- are present, then carbon dioxide will be released. If we have a quick look at this again, we can remember the ion here. It is negatively charged by 2. This means it has gained 2 electrons, which means remember, electrons are negatively charged, so the more electrons, the more negative something is. Alright, if any carbonates CO3 2- are present, then carbon dioxide will be released. Carbonates give off CO2 with hydrochloric acid. Let's put this into an equation, shall we? A carbonate plus an acid turns into carbon dioxide and water. To understand this a bit more, we will go into the little letters and numbers of things to see that everything is always, in chemistry, it makes sense. Nothing just vanishes. Everything stays. Let's count things. On this side, we have 3 oxygen. And then we have 2 hydrogen, 1 carbonate. And over here, we have the same. 1 carbon, 2 oxygen, 3 oxygen. So we have our 3 from here. And then we have our 2 hydrogens right here. We look, nothing is disappearing. Everything stays in the equation. This is carbonate, this is our acid. Oh, little reminder. Acid always is H plus, and hydroxides will be OH minus. So imagine a plus being acid, and minus being alkali for the normal stuff you see, like hydroxide. Hi, Roger Hobo. How you doing? Organic chemistry describes my farts. Ooh. Oh gosh, I'm not quite sure what farts is. I apologize. I hope you enjoy the stream. I apologize for any background sound. Hopefully it's not too noticeable. Hi, how you doing? You doing well? Now, let's go on the next one. Test for sulfates with hydrochloric acid and barium chloride. Sulfate ions, 1 sulfate, 4 oxygens with a -2 charge, produce a white precipitate. Imagine this as a just sort of color that fills the solution. So if we had a clear beaker and it was filled with water, and then we did some sort of experiment and it formed a white precipitate, then the solution would turn white. Rojo says, this reminds me of A levels. I do not want to remember. Oh, this is very basic. So this is just going back to like GCSE sort of level. It's always good to have a little bit of memory of these sorts of things, isn't it? Always good to have a little bit of memory. The more you do things, the more you remember them. And this is why I know the name of every single League of Legends champion and a general gist of what each champion does. Oh gosh, I need to play less League. And Valorant. Oh, I really would like to play more Valorant and League on stream, but my computer just can't run it. And I don't have a second monitor, so I wouldn't be able to check chats and that sort of thing. And for me, the biggest thing about streaming is talking and interacting with people. So if I lost being able to see chats, that would just sort of ruin it for me, you know? But who knows? Maybe one day I can have a second monitor. Mm. Mm. Now, let's go on to testing for sulfates. To test for a sulfate, you need to add dilute hydrochloric acid followed by barium chloride solution, BlCl2. Ba2+, these are barium ions, and they're aqueous. Then, if you add sulfate ions, that turns into barium sulfate. A white precipitate of barium sulfate means the original compound was a sulfate. The hydrochloric acid is only added to get rid of any traces of carbonate or sulfate ions before we do the test. Both of these would also produce a precipitate, so they'd confuse the results. So, we always add our dilute hydrochloric acid just to get rid of everything beforehand. Les says, maybe check chat from a phone or laptop or something like that. Yes, what I used to do was what I still do when I do play games, when I get my game redeems. I have my Twitch chat on my phone, but the problem is I multi-stream. I stream on Kick and I also stream on YouTube. So I don't want anyone to think I'm ignoring them or anything like that. I have a Chromebook, but it can't load all the 3 things at once, and it just doesn't work. So, yeah. Thank you for the water consume. Let me just have a little sip. I appreciate it. Well, now, let's go on the next one. Instead of using hydrochloric acid, we will be using nitric acid for this next one to remove all the other things in the test that could change our results. So, testing for halides. Chlorine, bromide, iodide. If you remember, these are all in group 7. And in group 7, we have the reactivity. That at the group 7, the reactivity goes down as you go down our column. So, chlorine is the most reactive, and then bromine is less reactive, and iodine is even less reactive. So, the special thing about this one is silver nitrate solution. Alright. A chloride ion gives a white precipitate of silver chloride. A bromide ion gives a cream precipitate of silver bromide. An iodide ion gives a yellow precipitate of silver iodide. Again, the acid is added to get rid of the carbonate or sulfite ions before the test. You can use nitric acid in this test though, not hydrochloric acid. So we have our silver, positively charged, our chloride, negatively charged, to form a neutral silver chloride. And yeah, these are all gases. Wait, hold on, let me just zoom in. Oh no, they're all solids. These are solids in this case. Now, it's just the same. White, cream, yellow. So chloride, bromide, iodine. We can imagine to get this into our memory, we can also imagine chloride being at the top, and as you go down the column, things get darker, which is also the case in this test. For example, remember chlorine, it's our green, and then we have our brownie ready, and then we have our darker one. Oh gosh, I missed a page. Let's go back to gases and water. Alright. These ones will be actually very useful in just day-to-day life and knowing things. So, there are lots of clever ways of testing for different gases, but dipping your finger in a liquid and saying that it's wet is not the best test for water. Don't worry though, there's a more scientific method for that too. There are tests for 5 common gases. Number 1, chlorine. Damp blue litmus paper. Chlorine bleaches it. It turns it from blue to white, but it may turn red for a moment first. This because a solution of chlorine is acidic. Chlorine is acidic. Hi Flynn Glazer. Is Brochado teaching us? That's an interesting name, Brochado. Yes, we're just going over some basic chemistry today. We're going over tests for gases and water at the moment. Let's read again the chlorine. Blue litmus paper is also often used in experiments to test if something is acid or alkali. If it is alkali, it will be blue. And if it is acid, it will go to white, with a little red stage in the middle. Now, second one, oxygen. Oxygen relights a glowing splint. So, if you have let's just say a matchstick without the thing at the end. If it is slightly burning but there's no flame, and you put it over oxygen, a big flame will appear. And this is because oxygen burns. Now, carbon dioxide. Carbon dioxide turns lime water cloudy. Just bubble the gas through a test tube of lime water and watch what happens. This is different to a precipitate. No, it is not. No, it's not different. It is the same. Let's zoom into our little diagram here. We have the gas that we bubble into the lime water. The lime water will change color. Will go all cloudy and not clear. Alright. Hydrogen. Hydrogen makes a squeaky pop with a lighted splint. The noise comes from the hydrogen burning with the oxygen in the air to form water. Now, ammonia. Ammonia turns damp red litmus paper blue. It also has a very strong smell. Now, with ammonia, this is opposite to chlorine, because chlorine is acidic and ammonia is alkali. So, ammonia will turn the paper blue to show that it's alkali, and chlorine will turn it red and white to be acidic. This is another test that is quite important. Wet copper 2 sulfate is blue, and dry copper 2 sulfate is white. Copper 2 sulfate crystals can be used as a test for water. When copper 2 sulfate is bound to water of crystallization, see, it forms lovely blue crystals. But if you heat the blue hydrated copper sulfate crystals, it drives the water off. This leaves a white anhydrous copper 2 sulfate powder, which doesn't have any water bound to it. But if you then add a couple drops of water to the white powder, you get the blue crystals back again. So, if you want to test for water, all you need to do is add anhydrous copper 2 sulfate and see if the white powder turns blue. This test will tell you if water is present in a solution, but it won't tell you if the water is pure. When a sample is pure, it means it's only made up of one substance. This means it has set, defined physical properties like a boiling point and freezing point. So, pure water will always boil at 100 degrees Celsius and freeze at 0 degrees Celsius. And if there are other things inside it, and if it's not pure, this may change. This may change the boiling point and freezing point. So let's look at this again. Does this remind us of crystallization? Because it's the same concept. We have our evaporating dish here. We have our little crystals here. But then it would have been a lot more water. Let's imagine this is a solution of copper 2 sulfate and water. If we heated this up, all the water would evaporate, forming these little crystals, and if we kept on evaporating, it would turn into this little white powder. Now, let's skip energy transfers. We don't need alpha changes. Alright, let's go to organic compounds. This section is all about organic chemistry. This means molecules that contain carbon. Now, let's go through types of formulas. There are general formulas, empirical formulas, molecular formulas, displayed formulas, and structural formulas. Let's go through what each one is and what it shows you. So, a general formula. A general formula is an algebraic formula that can describe any member of a family of compounds. So, for ethene in this case is an alkene. CnH2n. Hi, Hadakayas. How you doing? You doing well? We're doing some chemistry today. Yes. Relaxing chemistry ASMR, bro. Now, empirical formula. The simplest whole number ratio of atoms of each element in a compound, and you cancel the numbers down if it's possible. CH2 in this case, for ethene. Now, the molecular formula. The molecular formula is the actual number of atoms in each element in a molecule, which is C2H4. So, hi Rabbit, how you doing? You doing well? And then we have the displayed formula, which shows how the atoms are actually arranged in the molecule. We are going to zoom into this one for a little bit more detail. So, here it is ethene, and if it has an ene at the end, this means the carbons have a double bond, which means, hypothetically, you could add some more hydrogens to it. But if it's an ethane, then there would be more hydrogens and a single bond between those. Just gotta remember, ene equals the carbons are double bonded. Ane means that they are not double bonded. Now, structural formula. The structural formula shows the arrangement of atoms. carbon by carbon with the attached hydrogens and functional groups. For this would be CH2, CH2. Mm. Claire said, yeah, I had to take medicine after work. Well, I didn't, but I should have. Go take your medicine now. Alright? Take care of yourself. I had a horrible headache earlier today as well, so I had some paracetamol. Make sure you eat and take care of yourself, drink water, all of those things. Okay? Now, compounds in a homologous series share similar chemical properties. A homologous series is a group of compounds that can all be represented with the same general formula. You can use the general formula to work out the molecular formula of any member of a homologous series. Now, go back to our general formula here. We have CnH2n, and the n's here can all be changed. Hi, Sheeta. Thank you for the water consume. I'll do that now. Oh. Thank you. Alright, let's continue. A homologous series. Oh no, I've already read that. You can use a general formula to work out the molecular formula of any member of a homologous series. For example, alkanes are a homologous series that only contain carbon and hydrogen atoms. The general formula for alkanes is CnH2n plus 2. So, the first alkane in the series is C1H2 times 1 plus 2. This equals CH4. And the second is C2H2 times 2 plus 2, which is C2H6, etc. Now, we have to remember, this is the alkanes. This is the alkane series. I'm going to write, this is quite important, so I think I will write in chat. Actually, no, I don't have the small text. But yes, the difference, the alkanes formula is CnH2n plus 2, and the alkenes, the alkenes formulas are CnH2n. You see, for all alkenes, it says up there in the small text. Now, molecules in a homologous series contain the same functional group. A functional group is a group of atoms that determine how a compound typically reacts. This means that compounds in a homologous series often react in similar ways. These are the functional groups you need to know. First off, we have alkenes. Alkenes has the enes at the end, so remember the carbons double bonded. We have the alcohols, which have the OH at the end. We have the carboxylic acids, which have a double bond between oxygens and carbons, and these are bonded to a hydroxide. And then we have esters, which have a double bond between oxygen and carbon, and a normal oxygen bond. And we remember that R is used in place of the carbon chain that is attached to the functional group. Now, let's do some naming organic compounds. Organic compounds used to be given whatever names people fancied, but these names led to confusion between different countries. Luckily, chemists got together and came up with a system. Nomenclature is a fancy word for the naming of organic compounds. The IUPAC system for naming organic compounds was invented as an international language for chemistry. It can be used to give any organic compound a name using these rules as nomenclature. First off, you count the number of carbon atoms in the carbon chain. This gives you the stem. So, we have 1 carbon, it's meth. We have 2 carbons, it's eth. We have 3 carbons, that's prop. We have 4 carbons, that's bu. We have 5 carbons, that's pent. We have 6 carbons, hex, and so on. Now, the main functional group of the molecule usually tells you what homologous series the molecule is, and so it gives you the prefix or suffix. Okay, so homologous series, do you remember that? The alkenes, the alkanes, the alcohols, that sort of thing. Alright. Alkanes, the prefix or suffix is "-ane". Alkenes, it is an "-ene". Alcohols, it's an "-ol". Carboxylic acids, oic acid, esters, prefix, axial, or "-il" if it's a suffix, and then it's an analate. It's a bit hard to pronounce these two here. Now, we have. Let's skip the examples. Alright, let's count some things. Oh, wait, we have something else. If there's more than one identical functional group, use the di, it's 2, tri, 3, or tetra form before the suffix. For example, CH2, CH, CH2, CH3. The carbon chain is 4 carbons long, so the name is butane. Well, not butane, bute. The main functional group is the carbon-carbon double bond, so it is an alkene and the name will end in "-ene". Numbering the carbon chain so that one of the carbons in the CC group has the lowest possible number puts the CC group on carbon 1. This means that the systematic name for the molecule is but1-ene. Will we all understand this? Hopefully we can understand this. So we have a carbon chain, we number it 1, 2, 3, 4. So then we put the lowest possible number, puts the CC group on carbon 1. CC group, this is our double bond. We put our double bond here. Now, let's go to example 2. The carbon chain, this one is 3 carbons long, because we have 1 carbon, 2 carbon, 3 carbon. So, the step is probe. The main functional group is /OH, so the suffix is "-ol". Alcohol. Minus OH is alcohol. Then we number the carbon chains, and this puts the OH on carbon 1. This means the systematic name for the molecule is propane-1-ol. This molecule is often just called propanol. And I think we don't need to do no isomers. This is where we will be ending the stream today. But I hope you all had a lovely time here. This was different than usual. I hope that it was okay. I think tomorrow I will either be doing a biology one, or we might be doing a bit more chemistry, depending on how I'm feeling, and I'll look through all the chapters to see. So, I will be ending the stream on YouTube and Kick, and on Twitch I'll be streaming a little bit longer just to read out. But thank you all for tuning in. Have a great rest of your day, night, any time zone it